Hi folks, welcome to part 3 of the implicit differentiation lesson. So you'll notice that I skipped number 3 on the sheet. It's a fairly straightforward one, so you can just check out the written solutions. All right, so here they're giving us this relation, but something interesting is that we see that we have the constant in front of sine x that is not a specific number. Okay, so that means it can take on any value since there's no restrictions given on this a value. And they want us to also notice that 0, 0, regardless of the value of a, is always a point on this relation. So let's just check that real quick. So on the right-hand side, I've just got sine x here. So sine of 0 is 0. So regardless of what a is equal to, the right-hand side is always equal to 0. And clearly, if I input x and y equals 0 on the left-hand side, I'm also going to get 0. So regardless of how we change this parameter, 0, 0 is always going to be a point. So let's see what they want us to do. They want us to find a formula for the slope of the tangent to the relation at 0, 0. So that's telling us that it's probably not always the same as a changes. And then we want the equation of that tangent. All right, so let's see what happens. We'll take a look at b later on. So I want you to notice here that it's impossible to solve this problem explicitly because there's no way to solve for y in this question here because we have both a y and a y squared. So that means we have to use implicit differentiation. All right, so I'm going to take the derivative of both sides with respect to x. So I'm going to take the derivative of, and I'll kind of distribute out, I'll use that subtraction rule. So I'm going to have to take the derivative with respect to x of x squared minus the derivative with respect to x of 2xy squared minus the derivative with respect to x of y, and then the same on the other side of a sine x. All right, so we've got a couple of easy ones here, namely this first one. So derivative of x squared with respect to x is just 2x, nice and easy, minus, this is where we have to be careful because we've got 2x times y squared, so we're going to have to use the product rule here. So let me use brackets here just to make sure I don't forget to apply that negative to everything that comes out of that derivative. So let's take the derivative. Derivative of 2x is just equal to 2 times the second function y squared plus the first function 2x times the derivative of y squared, but remember with respect to x, so I'm going to have to use a chain rule. So first I'll take the derivative of y squared, that's just 2y, and then times the derivative of y with respect to x, which I'll just write as y prime. All right. Now, minus, well, this is a nice easy one because the derivative of y with respect to x, again, I can just represent using y prime. And now we can take the derivative of the right-hand side. Remember that a is just a constant, so it's just going to be a times the derivative of sine x, which is just cos x. All right? So now that we've taken the derivative implicitly, we see that we can bring together all the terms that have y prime, and we'll bring everything that doesn't have y prime to the other side. All right, so this negative is just going to be distributed to everything, so I'm going to keep this whole thing. Okay, but remember we have to apply this negative, so I'm going to have negative 4xy y prime. I still have this minus y prime equals, so I have my a cos x. All right. And let's see what I'm bringing to the other side. Well, I'm bringing this 2x to the other side, so minus 2x. And here I have this minus 2y squared, which I'm going to bring to the other side. So that's going to become plus 2y squared. All right. And then finally, I can factor out the y prime. And what am I going to have left? Negative 4xy minus 1, which I'm going to divide to the other side. So you notice here I'm skipping steps. If you need to write these out, I would strongly recommend that you write them out. Okay, so what do we have? We have a cos x minus 2x plus 2y squared all over negative 4xy minus 1. All right. And what we want is we want the slope of the tangent at 0, 0. So in other words, what we want is we want the derivative evaluated at 0, 0. So remember, this is the notation I showed in the second video, sorry, that I showed in the first video when we're evaluating the derivative at a point because we need to use both the x and the y values. All right, so let's see what we have here. Well, cos of 0 is just equal to 1. So I have a. This is going to be minus 2 times 0 is 0, plus 2 times 0 squared is just 0. This whole thing is 0 minus 1. So in the end, I'm just left with negative a. All right. So our formula for the slope of the tangent at 0, 0 is actually quite an easy formula. All right. And now they also want the equation of the tangent. Well, remember, this passes through 0, 0. So in other words, I know that the y-intercept is equal to 0. So the equation will just be y equals negative a, which is the slope, times x, plus, well, 0, because my y-intercept is 0. And so there we have it. So what we've determined by first differentiating implicitly, solving for y prime, and then evaluating at the particular point we're interested in 0, 0, we found a formula for the slope of the tangent at this point and a formula for the equation of the tangent at that point. All right, and I think what we should do is take a look at this function and see what it looks like and check to see that our answer does make sense, okay? And that's exactly what they ask us to do here. So let's go to our graph. So I've already got the equation. So let's see what this function looks like, okay? And we see that, oh, again, I misspoke. I really should have been saying what this relation looks like. So this definitely, is a relation, okay? Kind of interesting. Now, if I take a look at 0, 0 before plotting it, hey, look at that. It looks like the slope of the tangent is 0 here, okay? Now, that makes sense because if I look at my formula that we had determined for the equation of the tangent line, well, we just see that when x is equal, when a is equal to 0, I'm just going to have y equals 0. In other words, a horizontal line, okay? Which is what we see there, okay? Now, let's see if this line that we determined works when we start to change the a value. And as I change the a value, we see that the function changes. But notice the tangent line. It's always tangent to the curve at 0, 0. Okay, so it looks as though, oh, pretty interesting the way this thing behaves. Okay, oh, kind of almost starts to look like a peanut there. Okay, let's see what happens as we go into the negatives. But again, I want you to look at that tangent line. We notice that it's always tangent to the curve. Okay, let's see. Okay, yeah, it's still always tangent. So it looks like our formula does work. All right, now just for the fun of it, I'm going to sort of say, you know what, why don't you increase, here we're only looking at a from negative 10 to 10. Let's see what this function looks like when we allow a to take on other values. So I think I say going from negative 1,000 to 1,000, all right? So let's see what happens here. Oops, I forgot to change this one here. So let's put it... Oh, sorry, I think I accidentally put the steps. This is not what I wanted. I want to keep that as 1. And let's put this to 1,000. Sorry about that. Okay, so just like before. But now, whoa, 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 look what happens. So this function behaves as we expected, but then as it gets larger, look at these things almost start to behave like bubbles that start to appear and bubbles that start to be created. Okay, there you go. And you see that the further I go, the more of these bubbles seem to get created. Okay, so you can almost see here how one can use these relations to start to create animations. This almost looks like bubbles being created, in a bubble bath, there you go. And we see that even the other side, the same thing starts to happen. All right, and in fact, I guess we can play this a little bit, and we see that quite an interesting little function. So again, interesting to see how you can use these relations to create these animations. All right, but in the end, the main thing, okay, let's keep in mind what we started off to show was that the the equation of the tangent line that we found works, because regardless what we choose for a, we see that this always gives us the correct tangent line at 0, 0. Okay, that's it for this one.